Okay, I would like now to do an example where there's a mismatch in the numbers. So here you have a 3 and a 2. Remember that I had told you, I had pointed out that those numbers need to match if I'm going to use this formula. This formula for finding the Laplace transform of a translation. These numbers need to match. Otherwise, you cannot use the formula. So there's a mismatch here. A mismatch. We would like to find the Laplace transform of this, but the formula cannot be used directly just yet. So we have to do some algebra trick, some modification in order to put it in the form where we can use the formula. Okay, so what we need to do is we need to force these numbers to be the same. The subscript for the u, that one we cannot really change that in any way. That has to stay a 2. The only one we have freedom to modify is the 3. That's outside. That one we can change. So ideally, we would like a 2 there, right? We would like that to be a 2. So what we can do is then write a 2 and then modify it, but you want to make sure that you don't really change the whole thing. So you put in there what is missing so that the value is not really changed. So it's like you split up the 3 into -2, -1. And then this is u2t. And then in this one, you do exactly the same. I cannot change that 3, but I can change that 2, which is outside. And ideally, I would like a 3 right there, not a 2. So I'm going to put a 3 and then modify what I just wrote so that I don't really change the original value, which is t minus 2. So I add a plus 1. And that way, nothing is really changed. Okay, now what we're going to do is we're going to distribute. When we're going to think of t minus 2 as an entity that is inseparable, we're not going to separate that because we want it to stay like that, so we can use the formula. And then the 1. And similarly here, the t minus 3, we have to treat it like a single entity when we distribute. So now, let's distribute. So u2 times that would be t minus 2 u2t, and then distribute into the minus 1, it would be minus u2t. And now distribute this here. So u3 times this, and remember there's a minus in front, so minus t minus 3 u3, and then multiplying these two, you get 1 u3, and then there's a minus in front that also affects this, so it will be minus u3t. And now the numbers match perfectly. That there and that there, and now we can use the formula. Let's take L on both sides. It's going to be the Laplace transform of f of t is, and using the linearity, I can just find the Laplace transform of each piece. So this is the Laplace transform of t minus 2 u2t minus the Laplace transform of this one, Laplace transform of u2 minus Laplace transform of that one, t minus 3 u3 t, and then minus the Laplace transform of the last one. Okay. Now we can apply the formula here. That was the whole point of doing this. We apply the formula here. What does the formula tell me? The formula tells me that the Laplace transform of this translation the Laplace transform of this translation. So you have the u in the translation. The way I wrote it is backwards. I put the u second and then translation first. But either way, if you want to find the Laplace transform of that product, the answer is that is going to be e to the negative cs, where c is the number, c in this case is the 2, times the Laplace transform of the function disregarding the translation. So it will be e to the negative 2s times the Laplace transform of the function, the one that is next to the u, disregarding the translation. So it will be t minus 2, but disregarding the minus 2 part, so it's just t. So the Laplace transform of t. Okay, then this one we'll do in a minute. I'm just going to copy that one. Okay, and here we have another translation just like this one. And the only difference is that it is a 3. Otherwise, it's exactly the same. It's exactly the same function that is being translated. So this is going to be e to the negative 3s Laplace transform of t minus Laplace transform of u3t. Okay. And now we look these up in the table of Laplace transforms. So Laplace transform of t, right here, it is t to the n with n equals 1. So if this is the function, this is the Laplace transform. So with n equals 1, this is 1 over s squared. If n equals 1, this is 1 factorial, which is 1 over s squared. Okay, so that means this is equal to e to the negative 2s times 1 over s squared. Now, the Laplace transform of u2, and by the way, we should write down the number that we used. This was formula number, row number 3 in the table. Okay, row number 3. And okay, now we will look in this one up. That one is this one right here, number 12. So the Laplace transform of u2, u sub 2 is going to be e to the negative 2s over s. E to the negative 2s over s, or times 1 over s, same thing, exactly the same thing. So it is this one, e to the minus 2s over s. So we use number 12. And now the next one is exactly the same as this one, but with a 3 instead of a 2. So this is minus e to the negative 3s. Okay, no, sorry. The Laplace transform of t is this thing. Yeah, so it's the same as this, but with a 3 there. This one stays the same because this is a Laplace transform of t. So that is still 1 over s squared. 1 over s squared minus the Laplace transform of this one, the Laplace transform of that one, u3, is e to the minus 3s over s. E to the minus 3s over s. Okay, and that is the answer. Now, you could just leave it like that, or we can just rewrite this a little bit and write everything over a single fraction, which we're going to do. So this is e to the minus 2s over s squared minus. Now, I want the denominator, you see the denominators are s squared, s squared, and s. If I want the common denominator, that would be s squared. So I will multiply top and bottom by s. So I get s squared on bottom. So this is s e to the negative 2s over s squared. This one is already s squared, so minus e to the negative 3s over s squared minus what? Minus e to the minus 3s times s over s squared, because you have to multiply this one by s, top and bottom. Okay, and now let's put everything under in a single fraction and collect the terms that have the same type of e to the negative 2s and e to the negative 2s. I can combine those. So the whole thing, first of all, is going to be over s squared. And then combining these two, this is um, e to the minus 2s, negative 2s, and then put here when you factor it out, you get 1 minus s. And then from here, you factor out the e to the negative 3s in the negative, you end up here with 1 plus s. And that is a better looking answer. Okay. So that was the last example of finding the Laplace transform of a function that has discontinuities, because this is a piecewise defined function. We graph stuff like that. This is a piecewise defined function. It's discontinuous. Now we're going to do some examples where we find the inverse Laplace transform. So now we're going in the opposite direction on the table. Okay. So first, this is the easiest example. The easiest example is when you can find it directly like that in the formula, in the table, without having to modify anything whatsoever. So in the table, in the column for the Laplace transform, capital F, we're going to look at something that looks just like that. And if you see, the one that looks the most like that is this one right here. It is precisely that one where n equals 3. Indeed, because you have, if n equals 3, you have n, that you have 3 factorial on the top and the exponent will be 4. So that matches perfectly. N equals 3 and a equals 2. Okay, so looking at the corresponding inverse Laplace transform, it will be this thing where again n equals 3 and a equals 2. So this problem, we got the answer right away. So little ft, which is the Laplace transform of capital F, is going to be, according to that, when n equals 3, t cubed e to the 2t. A equals 2. And that's all. That is the answer for that problem. So the first example was easy. Now we're going to do some examples where not so easy. That means you cannot really find them right away on the table of Laplace transforms. So here's this one. But this one is still not too bad. This one is not too bad. Okay. So if you look this one as is on the table of Laplace transforms, you're not going to find it. You have to do some algebraic manipulation before you can find it. So the first thing we're going to do is pull out the e part. So this is e to the negative 2s times 2 over s squared minus 4. And the reason we want to pull out the e part out of there is because if you remember the formula, if we're trying to find the Laplace inverse, you see we have a formula for the Laplace inverse of a function, an expression that has some exponential factor, e to the something times something else. If we could write the thing that we want to invert in this way, then we can use this formula to find the Laplace inverse. Okay, so this part right here is this part, and then that part is that part. So according then to this formula, the Laplace inverse of this is going to be what? Is going to be u2 is going to be u2 times what? The Laplace inverse of this function right here, but not evaluated at t, evaluated at t minus c, which in our case c is 2, so evaluated at t minus 2. So that means I need to find the Laplace inverse of this function right here, which is this one, and evaluate it not at t, but at t minus 2. So I need to find the Laplace inverse of this function and evaluate it not at t, but at t minus 2. That's what that formula tells me. Okay? So then we need to find what that is. And hopefully that is in the table. So let's look something that looks very similar to that. Look that the top is a constant. So it cannot be this one because the top of this one is a variable, s. So it has to be this one. The top is a constant. And note that the constant in this table has to be precisely the square root of the bottom, or the bottom constant has to be the square of the top. In this point, that is the case, so that's good to go. If it were not the case, then we would need another algebra trick to force them to be that way. In this case, we're lucky, we don't have to do that, but we'll do some examples later where we have to. Okay, so then this is going to be, so we said this is number what? This is number, what was this one? What's this one right here? 7. So that's going to be the hyperbolic sine of AT, where A is 2. So this is going to be hyperbolic sine of AT, where A is 2, so 2t. But however, it's not 2t because we're not plugging in at t, we're plugging in at t minus 2. So it's actually then, instead of 2t, is 2t minus 2. And that is the answer. Now, if you have never seen hyperbolic sine and hyperbolic cosines, well, it's not really hard. Um, this is what hyperbolic sine means. Hyperbolic sine is a new function that is defined in terms of e by this formula. So that's all it is. Hyperbolic sine is e to the t minus e to the negative t over 2. And hyperbolic cosine is e to the t plus e to the negative t over 2. So really, um, these are functions that are just defined in terms of e by these expressions there, and that's all. So you see there's not even any sine here or cosine, so they're not really trig functions, but they have some properties that are similar to sine and cosine, such as, for example, the derivative of the hyperbolic sine is the hyperbolic cosine. But you don't really need to know a lot about these functions. Just know this, what they are, which is this, and know that you can leave the answer like that. If we eventually later need more properties, then I will tell you what those are, but for now we don't really need them. That's it. That's the answer. Okay, and this is the last example. This is the most complicated one, so I left it for last. And but again, it's not really too bad either. It's not like we're gonna need 2 pages. Although there are some problems later where they're long and tedious. But this one yet is still not too bad. Okay, so first thing is to find the Laplace inverse of this. Again, if you try to look this up in the table, you're not gonna find it. It's too complicated. Then the table of the Laplace transform is just like basic functions. Alright, so first thing is pull out the e part, just like we started the other one. So this is e to the negative s times, and then what is left? S minus 2, all that over s squared minus 4s plus 3. Okay, that's still not in the table. However, the bottom factors, you can easily factor that. So that means we can break up this rational function into simpler expressions using partial fractions. So let's factor it. This is e to the negative s times s minus 2 over s minus 3 s minus 1. So that's how that factors. So that means if you use partial fractions, this can be decomposed into two fractions, a over s minus 3 plus b over s minus 1. Okay, now let's figure out what a and b need to be. So let me do that in black. So this is going to be a over s minus 3 plus b over s minus 1. That's supposed to be s minus 2 over s minus 3 s minus 1. Okay, now we're going to multiply by that, both sides. So this is going to be a times s minus 1 plus b s minus 3. And then when you multiply here by this, that just goes, and you end up with s minus 2. Okay, so multiply both sides by s minus 3, s minus 1. That's what you get. Then plug in numbers that make one term equal 0. And by the way, this method of figuring out what a and b are is called the Heaviside cover-up method. So the same guy, the Heaviside, that invented that the Heaviside function, that introduced them in this theory, is the same guy that came up with this method. So this method is called the Heaviside cover-up method for partial fractions. For partial fractions. Okay, so plug in 1, that's going to make that 0, and we're going to get b times 1 minus 3 equals 1 minus 2. So this means negative 2b equals negative 3. No, wait a minute. 1 minus 2 is not negative 3. That's negative 1. Okay, negative 1. And then dividing, we're going to get that b equals 1 half. B equals 1 half. And now plug in s equals 3. To cover this one up, we get 0 here. You're going to get a 3 minus 2 is 2. A times 2 equals, plugging in 3 here, you get 1. So it happens that a actually is also 1 half. So then we can continue solving the problem. So going back here, we're going to get capital F of s equals e to the minus s times, so you're going to have 1 half over s minus 3 plus 1 half over s minus 1. Now we can pull out the 1 half from both sides, from both, factor it out, put it in here. So 1 half e to the minus s, this is 1 s minus 3 plus 1 over s minus 1. And lastly, I'm going to distribute this. This is going to be 1 half e to the negative s times 1 over s minus 3 plus 1 half e to the minus s times 1 over s minus 1. Okay, now we are ready to invert this. Now we're ready to invert this. Okay, so Laplace inverse of capital F is going to be, we're going to need to look at the table of Laplace transform. And we're going to be using that formula as well. That formula, which one? This one. This one. We're going to invert something that has e to the, that has an exponential in there. Okay, so there it is. So the 1 half stays there. That doesn't bother. But applying the formula, we're going to get that this is c, and the c in this problem is negative 1. Sorry, it's 1, because we have e to the negative s, so that means the c is 1. So this is going to be u1 times the Laplace inverse of this, that's what the formula tells us, times the little f is the Laplace inverse of that, but not evaluated at t, evaluated at t minus c. So we need to find the Laplace inverse of this and evaluate it not at t, but at t minus 3. Sorry, at t minus 1. So times the Laplace inverse of this, evaluate it not at t, but at t minus 1. And now this one is very similar. This is going to be 1 half u1 t times the Laplace inverse of this, evaluate it not at t, but at also t minus 1, because the c is 1 in this problem. That's what the c is in both of them. The exponent, that c is 1. Okay, almost done. Now let's look that one up. Laplace inverse of this This is, what is that? 1 over s minus 3. 1 over s minus 3 is number 2 right here, where a equals 3. So this is going to be e to the 3t. E to the 3t. So this is e to the 3t, but not evaluated at t, evaluated at t minus 1. That should be a minus. T minus 1. And the next one, the inverse Laplace of this one, where a equals 1, would be e to the t. Let me see, is that supposed to be a minus? No, it should not be a minus 3. That should be just, I thought for a second there should be a minus, but there's no minus. Uh, if you have a s minus 3 here, it's just e to the 3t. Okay, there's no minus, it's a mistake. Okay, that I just fixed. All right, and lastly, this one is going to be e to the 1t, but not evaluated at t, evaluated at t minus 1. And that is the answer. And let me not forget about writing the formulas from the Laplace transform table that I used. We used number 2. That was the only one that we used this one, of course. This one is the one we keep using over and over. So 1 and, sorry, 2 and 13. We use number 13 and we use number 1. Okay.